In the next few minutes, I'll explain what cache memory is, why it matters, and how data gets organized in it using techniques like fully associative mapping and direct mapping. Let's dive in. So, what exactly is cache memory? Picture a small super-fast memory space sitting right between the CPU and the main memory. It's the job of the cache memory to hold data that the CPU uses all the time. Why? Because fetching data from the main memory is slow and the CPU needs quick access to keep things running smoothly. Here's how it works. The CPU checks the cache first. If the data is there, it's called a cache hit, and the CPU grabs it instantly super fast. If the data isn't there, it's a cache miss, and the CPU has to get it from the slower main memory, which makes which takes more time. By storing frequently used data in this fast little memory, cache speeds up processing. But how does the data get into the cache? That's where cache mapping techniques come in. Cache mapping is all about deciding how data from the main memory gets stored in the cache. The main memory is huge, but the cache is small and fast, so we need a smart way to link specific memory locations to spots in the cache. The goal is to have quick access to the data the CPU needs most. There are three main types of cache mapping, namely the fully associative mapping, the direct mapping, and set associative mapping. Let's start with fully associative mapping. In this technique, any block of data from the main memory can go into any spot in the cache. Think of it like a library where you can put any book on any shelf. Total flexibility. This reduces conflict misses, where data fights over the same spot because nothing is logged into a fixed place. But here is the catch. To find the data, the CPU has to check every single cache line, like searching hardware and time. The CPU has to check every single line, like searching every shelf in the library. That takes more hardware and time, especially if the cache is big. So while it's great for avoiding conflicts, it's best for smaller caches due to its complexity. Now compare that to direct mapping, which is simpler and faster. Here, each block from the main memory maps to one specific spot in the cache based on a formula like block number modulo cache size. It's like assigned seating in a classroom. Every student has their own chair. This makes it quick to check just one spot, but if multiple blocks map to the same spot, they can overwrite each other, causing conflict and more cache misses. So it's efficient for speed, but less flexible than fully associative mapping. To wrap up, cache memory and its mapping techniques are vital for fast computing. Fully associative mapping gives flexibility but can get complex, while direct mapping is quick but risks conflicts. These trade-offs shape how we design efficient systems. On this note, I'd like to hand it over to my fellow colleague, Makafui.
Taking over from where my colleague stopped, I'll be talking about set associative mapping, a compromise between direct and fully associative mapping, which I've already been speaking about. Memory blocks map to set, not specific lines. It also reduces collisions compared to direct mapping. I'll be talking about the structure of the mapping. Cache is divided into sets with multiple lines. Block maps to a specific set, not a fixed line. Uses index that's set selection, tag, block ID and offset. So about the structure, the cache is divided into sets and each set contains multiple lines. A memory block map to one specific set based on the address, but can go into any line in that set tag, which helps identify if a block is present. So that's about the structure. I'll be talking about the advantages and disadvantages. So about the advantages, fewer conflict misses than direct mapping, better space usage than direct mapping. So set associative mapping reduces the chance of two blocks conflicting, so there are fewer catch misses. And with the disadvantages, more complex than mapping and slower due to multiple tile comparison. So it's more efficient than direct mapping to bar, slightly slower due to the need to search multiple lines in a set. And also the hardware needed is more complex than the direct mapping, which that's the disadvantage people face due to all these things. Then I'll be giving an example. So let's say we have eight memory blocks, four sets in two lines per set. So block zero maps to set zero, then it also maps to line zero or one, and block five also maps to set one, and it also to line one, line zero or one. If set zero is full, a replacement policy like least recently used decides with time to replace this. It's accessed by content instead of address, performs parallel comparisons for lookup, and used in TLBs and catch tag stores. So I'll also be talking about the uses and the benefits and its advantages. So about the advantages, fast data lookup via parallel search, efficient for small, frequently accessed data. And the uses, they are used for TLBs, network routing, pattern matching. So about that, the main benefit of associated memory is speed, since it searches all entries at once. It's ideal for tasks that require quick data lookup. And I'll be talking about the bank memory. So the memory is split into independent access bank, which enables parallel memory operations and reduces access latency and increases throughput. So there are more to read on it, but I'm just making it brief. And I'll be also talking about the practical use. It's used in multiple core CPUs, GPUs, drums, allows reading from one bank while writing to another, and must manage bank conflicts to ensure performance.
Still on the cache mapping techniques, I will talk about effect of hit ratio on average access time and cache in virtual memory systems. Effect of hit ratio on average access time. Hit ratio represents the portion of memory accesses found in a cache. Also, the hit ratio is a measure of the effectiveness of the cache memory in serving requests from the CPU. Cache hits. It is the percentage of requests that are successfully retrieved from the cache. It occurs when the CPU requests data from the cache memory and the request is successfully retrieved. An example is if a website receives 100 requests and the cache serves 80 of them, the hit ratio is 80%. Cache miss. A cache miss happens when the CPU requests data or instruction from the cache memory, but then the requested item is not found in the cache. Since the requested item is not found in the cache, it cannot be retrieved, which then becomes the vice versa of the cache hit. Average access time. It is the average time it takes to retrieve data, considering both cache hits and cache misses. Effect of hit ratio on average access time in terms of performance. When the hit ratio is high, it leads to faster loading time for users, as data is retrieved from the cache. When the hit ratio is low, it results in slower loading time, as more requests requires accessing the slower origin server. In terms of resource utilization, when the hit ratio is high, it reduces the load on the origin server, as it's handling fewer requests when there is no strain on the origin server. When the hit ratio is low, it puts more strain on the origin server, potentially requiring more resources to handle the increased load. Factors affecting hit ratio, which then causes an effect on the average access time. 1. Cache size. Large caches can store more data, potentially leading to a higher hit ratio. However, excessively large caches can also lead to increased memory usage. Cache invalidation. If data is invalidated too frequently, it can lead to a lower hit ratio. How data is updated or removed from the cache is very crucial. Access patterns. Frequently, accessed data is more likely to be found in the cache, resulting in a higher hit ratio. The formula for finding average memory access time. The average memory access time can be calculated using the following formula. Average memory access time is equal to, into bracket, h times tc plus another bracket, 1 minus h times tm, where h is the hit ratio between 0 and 1, tc is the cache access time, and tm is the main memory access time. Also, the formula for hit ratio is equal to hit divided by the hit plus miss, where the hit is cache hit and miss is cache miss. Now to the cache in virtual memory system. Virtual memory. The virtual memory uses virtual addresses mapped to physical memory via page tables, where the page table is a data structure that maps virtual addresses used by processes to their corresponding physical addresses. Cache. The cache stores frequently accessed data to speed up memory access. The purpose of a virtual memory is to extend the apparent size of main memory by using disk space as an extension of the random access memory, the RAM. And the purpose of the cache is to speed up data by storing frequently used data closer to the CPU. The cache can be integrated in disk architecture in primary ways. 1. Virtually indexed, virtually tagged cache. The VIVT cache uses virtual addresses for both indexing and tagging. The VIVT cache is faster as it avoids address translation before access. The VIVT cache is prone to aliasing problem. The second is physically indexed, physically tagged cache. Cache access happens after address translation. VIPT cache ensures correctness and consistency. VIPT cache is slightly slower due to translation overhead. The third is virtually indexed, physically tagged cache. The VIPT cache is a hybrid approach. Under the VIPT cache, indexing is done using virtual address, which is fast, but tagging is done with physical addresses, which is accurate. Most modern CPUs uses this method to balance speed and correctness. Cache and page tables. When there is a cache miss and data must be fetched from main memory, the system may need to consult the page table to translate the virtual address. This can introduce extra delay unless a translation loop-side buffer (TLB) is used to cache recent translations. The role of translation loop-side buffer. Translation loop-side buffer hits has fast address translation. Translation loop-side buffer miss requires page table work, which increases access time. To conclude, thus both cache hit ratio and translation loop-side buffer hit ratio are critical to minimizing the effective memory access time. Thank you.